All right, today we're going to talk about cardinality, which is a way that we can compare sizes of infinite sets. Now, this subject can be a little tricky because most of our intuition about how sets work turns out not to be very reliable in the infinite set case. So we're going to start off with a very simple example. And the question we're trying to answer is, how can we tell that two sets have the same size? So I'm going to put up a set of X's and a set of O's on the board, and then we're going to think about how we can tell if we have the same size for each. So I've put up some X's and some O's on the board. And if all I did was ask you, do they have the same number of elements, your kind of natural inclination would likely be to count them. We have 1, 2, 3, 4 X's, 1, 2, 3, 4 O's, and so we would say we have the same number of elements. But it actually turns out that if you approach the problem that way, you're making it too hard. Right? So what I mean is, remember, I didn't ask you how many elements we had in each set. I just want to know whether or not we have the same number of elements in each set. And I'd actually like to do that in the sort of most efficient way possible, right? I want to do that with the least amount of work and effort. Now, counting to 4 is not a lot of effort, right? But let's think about how could we determine that the two sets have the same size without counting. Right? Well, if we think about this for a little bit, one idea that might occur to us is to just show that we can pair them up. Okay, so notice the difference here. I've shown that we, in fact, do have the same number of elements in both sets because for every X, there's exactly one O, and I've shown that with this pairing, right? I've matched them up. And in the language of cardinality, what I've done is I've exhibited a one-to-one correspondence between the two sets. We can declare that we have the same size sets, and we can say that even if we don't report or know how many elements are in each set. Right? These two sets have the same size, they have the same cardinality, and that doesn't require that I tell you how many there are. Now, another name for this pairing, right, as we said, is a one-to-one correspondence, and what that means, it's a function that's both one-to-one and onto between the two sets. So just a quick sort of picture reminder of what those two things mean. So if I had a function that did this, sent this X to this 0 and this X to that O, this would be an example of a function that isn't one-to-one because I took two different points in the domain and I attached them or mapped them to the same point in the range. Okay, so that would be a failed effort at a one-to-one correspondence because it's not one-to-one. Now, an onto function means you get everything in the range. So if I had something like this, well, this would fail on 2 counts. First off, it's also not one-to-one because the bottom 2 X's get mapped to the same O. It also fails to be onto because the top O doesn't get matched up with anything. So I've left out some of the range, which means the function wasn't onto. Now, in some of our work in this section, you'll be required to actually take the one-to-one correspondence, like a formula for it, and show that it's both one-to-one and onto. But for a lot of our examples, it's going to be enough just to sort of give the visual pairing, like how we would do that one-to-one correspondence. All right, so Cantor was the first to recognize that this idea of separating, showing that two sets have the same size from counting the number of elements in a set, he was the first to recognize that that's a really powerful distinction. And we can apply it to the setting of infinite sets in a way that we could not apply counting, right? You can't count an infinite set, but you can pair the elements of an infinite set with another set. And so this idea of one-to-one correspondence, in some ways it's more fundamental than counting, and it allows us to dramatically expand the kinds of sets that we can talk about the size of. So let's take a look at our first, perhaps not so intuitive example. So our fundamental infinite set is the set of natural numbers, which are just the counting numbers. And at least at first, we compare all other infinite sets to the natural numbers. If we conclude that an infinite set has the same size as the natural numbers, the same cardinality, then we say that that set is a countable set, or sometimes countably infinite. Those mean the same thing. So what we're going to show is that the natural numbers, in fact, have the same cardinality as the odd natural numbers. So the odd natural numbers would be 1, 3, 5, 7, 9, and so on. And the reason I think this is not going to be an intuitive example is what we've done is we've taken the set of natural numbers and we've thrown out infinitely many numbers. Right? We tossed out all the evens. So of course, maybe a first pass through this, we would suggest, well, if you take a set and throw out infinitely many members, then surely you have fewer members. And well, it turns out that that intuition is not the right way to approach the problem. We have to rely on our definition. Can we make a one-to-one pairing or correspondence between the two sets? So the answer is yes, we can. So here's the pairing. For every natural number, I can associate one and only one odd number, and every odd number gets a natural number paired with it. Now, if we were pressed, we could write down the function. I take my natural number, multiply it by 2, and subtract 1. And I think if we check that, 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. So this does do the pairing that I exhibited just by matching them up. And it wouldn't take too much to show that this is both one-to-one and on-to. All right, so again, a lot of the examples in this chapter are not intuitive examples necessarily. And what we're doing, kind of similar to what one might do in probability when you're seeing some probability for the first time, is you're training your intuition to work better in the situation. All right, so if we do some examples and it turns out that you're really having a hard time believing that it's true, Cantor himself, the person who developed all of this mathematics, after one of his examples, famously wrote, "I see it, but I don't believe it." So you may find yourself in that position, and that is an okay, in fact, expected feeling to have. All right, so I want to do two more examples. I've already kind of sketched them up. One is to show that the set of all integers has the same cardinality as the natural numbers. Right? That's another one that you might think, oh, I don't know about that. For every natural number, there's the positive and negative version of that number in the integers. So it seems like, well, maybe there's twice as many integers, right? But that's not, again, not the way to look at it. So the way I'm going to show this is just by kind of showing how we would do the pairing. So we would go start with 0, and then go to 1, and then to -1, and then the 2, -2, 3, -3. So our pairing, it looks something like this. And although this one would be a lot harder to write down as a formula, we'll be content with showing that it's certainly reasonable this is a one-to-one correspondence, because every natural number gets one and only one integer, and eventually we get to every integer, right? Because we're going from inside out. Eventually I get to number 100 trillion, and there's a natural number there to pair with it. So this example is showing that the integers and the natural numbers, in fact, have the same cardinality as well. All right, it gets worse. And that is that we can show that the set of rational numbers still has the same cardinality as the set of natural numbers, so that in a sense, they have the same number of elements. Now this one is certainly the hardest of all to believe so far, because remember, the rationals are dense in the reals, and one of the consequences of that is that between any two real numbers you pick, there's an infinite number of rational numbers, right? So the entire real line, pick 2 points on the real line, you have infinitely many rational numbers between them. And we're about to show that, in fact, still the rational numbers have the same size as the naturals. And the way we're going to do that, there's a more analytic proof in the text. This is kind of a geometric version of a similar idea. But the reason I've drawn an XY axis up here is this is going to allow me to represent rational numbers as points on this axis. So remember that rational numbers are fractions. So we have integers m divided by n as long as n isn't 0. And what we're going to do is we're going to map each of the fractions to a coordinate point in the plane where the numerator is the x value and the denominator is the y value. So for example, all the integers would be here. So minus 4 over 1, minus 3 over 1, minus 2 over 1, minus 1 over 1, 1 over 1, 2 over 1, 3 over 1, 4 over 1, and so on. The point 1/3 would be here. And the point 1/2 would be here. The point 3/4 would be over 3 up 4, right here. Okay, so if we organize the rational numbers this way, every rational number is represented by a point. We get the negative ones on the left, positive ones on the right. And it's kind of similar to the example with the integers, except instead of going back and forth inside out, we spiral out. So we're going to have, right, each of these points will be a rational number. We have to be a little bit careful about lowest terms. Technically, if we came up against a point that we had already covered, like we had 4 over 2 and we had already gotten 2 over 1, then we would skip over that point. But the idea is to start, say here, and just list the numbers. And now my lack of artistic ability is shining through, but the idea is a sort of spiral out so that eventually we hit all the rational numbers. Right? So we've got, so far, our fundamental infinite set, the natural numbers, has the same size infinity, the same cardinality as the odd natural numbers, as all the integers, and even all of the rationals. So a good question at this point is, well, are there any infinite sets that have more elements than the natural numbers? And the answer is yes. Cantor showed that the real numbers, in fact, do have a larger, so to speak, infinity than the naturals. And that's coming next.